Good morning, sunshine. So let's talk briefly about how KBs are different than KAs. So the base dissociation constant is what a KB is. We're going to quickly review how to calculate pH of strong bases, and then we'll get into using KBs and calculating pH of weak bases. So same definition for strong is that there's 100% dissociation, so you make hydroxide concentration in the same amount that you make coming from the strong base. But sometimes when the strong base is divalent, meaning anything from the second group, so calcium hydroxide, barium hydroxide, or strontium hydroxide, that 2 on each of these makes double the amount of hydroxides, therefore you must multiply by 2. And that is the only time you ever do that. You'll never ever do that with strong acids. You only do it with these 3 divalent strong bases. So to determine the pH of 0.0048 molar sodium hydroxide, you'll do, first off, the concentration of hydroxide is as given, 0.0048 molar. This information you can use immediately to find POH, or the real quick shortcut is 14 minus POH, where the pH is negative log of hydroxide. And this is just something that minimizes your calculations. It's the same process, but 14 minus a negative log of 0.0048 gives you a pH of 11.68. And we're recording 11.68 because there are 2 sig figs in the concentration. The 2 decimal points on the back side represent the significant figures in pH, so it makes sense for a strong base to be that high as well. For weak bases, we set up our dissociation constant expression the same way we do with acids. We must react it with water and show how it interacts with water. Usually the Bronsted-Lowry definition is what's applying here. So we can see in this example up here, hydrogen ion from water is being donated here because water is the acid in this case because it's the stronger acid of the two reactants, and this is the base. So that's our BABA, right? It's the acceptor of the hydrogen ion, leaving Hb plus with a plus charge from the hydronium or from the proton, and then hydroxide being produced. So to write the expression, we take our concentration of products over our concentration of reactant. And that water is pure liquid, so we ignore it. So do the same equilibrium reaction with ammonia acting as the base and water acting as the acid again. Water is going to protonate the ammonia, making ammonium and hydroxide ion. So it's pretty simple in terms of how we actually show the reaction, but sometimes I'll actually have you label which is the base, acid, conjugate base. So if this is the base and this is the acid, ammonia makes ammonium, which is the, in this case, conjugate acid, and the acid makes the water makes a hydroxide, which in this case is the conjugate base. And you remember how those work. They are opposites because in the reverse direction, the ammonium would act as the acid and the hydroxide would act as the base in terms of donor and acceptor. So for the first example, we're going to solve for pH for a weak base. We know this is a weak base because this is not one of our 8 strong bases. We're going to actually write out the dissociation reaction, set up the KB expression, and then solve for pH from hydroxide concentration. So using the same example previously, setting up our ice here, and I'm going to modify my ice box to make it a little smaller. 0.010 molar for ammonia, 0 and 0 for both of our products. We know that we're subtracting ammonia by X. Water is a pure liquid, so we ignore it, and we are making X amounts of both products in ice. The KB expression is ammonium times hydroxide over ammonia. And I like to write it out every time just in case, but if you find that you can correctly do it every time, then it's fine for you to go ahead and write out your KB expression as is with X's. So that'd be X squared over 0.010 minus X equals whatever the KB for ammonia is. And so this is something you look up in the back of your book. You can Google online, but I'll go ahead and tell you this is 1.8 times 10 to the negative 5th. Notice that this is very small, and so then your first thought that pops in your head is, can you neglect x? Because you would like to probably get rid of the x value down here so you can simplify your math. Let's try. So if we assume that is 0, it does straighten up our math a bit, as x squared is equal to 1.8 times 10 to the negative 5th times the denominator of 0.010. Solving for x to give us 4.24 times 10 to the negative 4th molar, and that x represents our hydroxide if you look back in your table. So whenever you check this value, it does make sense to neglect. When you take the x and divide it by 0.01 molar, times it by 100, you get 4.24% ionization, which is our p-value less than, or x, the p-value less than 5%. So it is barely there, but it is negligible. So once you find your hydroxide concentration, you can use that information to find directly POH and then pH. So POH, I'll show the long form first. Negative log of hydroxide concentration, which is negative log of 4.24 times 10 to the negative 4th. That gives us 3.37. pH is equal to 14 minus POH. So 14 minus 3.37 to give a basic pH of 10.63. So the setup is the same like we've done every icebox. Make sure you check your neglecting of x at the 5% rule, and then understand what x is representing. In this case, it's representing hydroxide. That's important in terms of calculating the pH. So for this example, we're not starting off with the same types of information. We were first given morphine as a weak base. We're given the fact that we have 0.015 molar of morphine, but we're given the pH already. So if you think about it, what is pH really giving us? This is probably going to be giving us information about ions, and then your choice of ion here. Since it is a base, naturally when you see pH, you're like, oh, I'm making hydronium. But you can find the POH from the pH and find the OH hydroxide concentration, which makes more sense in the realm of the base world here. So this is actually going to be giving you hydroxide concentration to use in your icebox, and then finalize the Kb value. So let's set up our example first in terms of a generic base. Generic base is B plus water, and I'll draw it here for you to show your donation process. So you get Hb plus, where the proton has now pronated B, and hydroxide ion on the side. Since our initial value is given to us as 0.015 molar, water is irrelevant. You already know you have 0 both your products. At equilibrium, though, you know that a specific amount of B is going to be reacting. So I'm subtracting X, adding X, and adding X. And that specific amount of X that's reacting is going to be attributing to our pH. So I'm going to use pH now to find what X is. So if pH is equal to 10.19, then POH is equal to 14 minus 10.19, which is 3.81. If this is POH, hydroxide concentration is 10 to the negative POH, so 10 to the negative 3.81. That information is going to allow us to find hydroxide concentration to be 1.55 times 10 to the negative 4th molar. This information for hydroxide concentration literally gives us what X is equal to. And X is equal to hydroxide, and X is equal to both the products. So if I can plug that in to my Kb expression, I can actually solve for Kb. So this is 1.55 times 10 to the negative 4th. Again, 1.55 times 10 to the negative 4th. And this would be 0.015 molar minus X at 1.55 times 10 to the negative 4th. Plug those values into your Kb expression, which I'm hoping that you can set up for yourself right here, and you'll find the Kb expression is equal to 1.55 times 10 to the negative 4th squared over 0.015 0.015 because this second number is so negligible it's practically the same. And you get a final answer for Kb to be 1.5 times 10 to the negative 6. These last two questions here are for extra practice for you. I'm asking for you to solve for the pH of a solution given initial concentration, as well as the Kb value. The second one is a similar situation. Those are extra practices since you don't really have a problem set for just Kbs. The last thing I'm going to discuss on this video is the relationship between the acid dissociation constant and the base dissociation constant. So let's just kind of look at this together so that you can maybe make the link yourself before I give the final answer. Go ahead and set the Ka expression from this reaction. I would start off by writing the reaction fully out first though. So this is an acid. It donates its acidic proton to the water to give hydronium and an anion. And so writing out the Ka expression, you get hydronium times anion over HA, which is simple enough. We've done that a million times now. The second one I'd like for you to write is that for a base. And the base in this case, you might make the connection here, is the conjugate base of that acid that we have in the example 1. So it is now going to interact with water, and since it's the conjugate base, it doesn't have a proton to give. It actually is going to then be accepting a proton from water to give exactly the reverse reaction in the top one, HA plus hydroxide. So now we have water acting as the acid down here, and the anion acting as the base. Previously we had water acting as the base and the HA acting as the acid, representing the amphoteric nature of water. Go ahead and write out the Kb for this. HA is equal to, Kb is equal to HA concentration times hydroxide concentration over the A concentration, where water is a pure liquid again. So looking at these two reactions, you'll see there are some similarities, but thinking back to how you can manipulate K values whenever you add VCEs, think about for a second, what do you do to your K values? You might remember you multiply your K values. So if we take this information, add up our VCEs, you'll see that the HA is then going to write into the color free. The HA is then going to kind of be canceled out because it's the same on both sides. You'll see the water is summative. You'll see the A minus is the same on both sides. And that's about it. So the only remaining the things standing here are the waters. So we have two waters equilibrating to a hydronium and a hydroxide. Looking at the Ka and Kb expressions, I'm going to then multiply them to show you what this equals. So when you take hydronium, A minus, and HA times HA hydroxide and A minus, you'll notice similar cancellations occur. So the A minus is on top and bottom, it cancels, and the HA is on top and bottom, so it cancels, leaving us with only hydronium ion concentration times hydroxide concentration. This should resonate with you as the Kw constant. So it doesn't matter what the acid and what the conjugate base is, or even the base and the conjugate acid, as long as they're from the same pairing for conjugates or acid-base conjugate pairs, their Ka value and their Kb value will always multiply out to equal Kw. And you might remember Kw, and I'll write it if you don't, 1 times 10 to the negative 14th at 25 degrees Celsius. So this is one fact that will be very, very valuable to you when we start getting to acid-base chemistry as well as salt hydrolysis. So main point you should get away from this is that any conjugate acid-base pair will have a Ka times Kb equal to Kw. So if you ever want to solve for the other, then you're just going to have to take what you know, which is Kw, and divide to find what the Kb is. And that's it for this video.